I will start recording now. Okay, good morning, everybody. Welcome for this new seminar at the Instituto de Astrofísica de Andalucía here in Granada, in Spain. And today we will have the talk by Dr. Jacques Kluska. And he will talk about circumbinary disk around post-AGB stars. Do they form second-generation planets? Jacques did his PhD in 2014 at the IPIG Institute in Grenoble, in France, on infrared interferometric imaging of protoplanetary disk around young stars. He then moved to the University of Exeter in UK to study these disks using a multi-instrumental approach at high angular resolution. Finally, in 2017, he moved to Belgium to KU Leuven to work on disks around evolved binaries that are very similar to disks around young stars. In 2020, he obtained a grant from the Flemish Research Council to observationally characterize these disks and investigate if planet formation is possible in such an exotic environment. So thank you very much, Jacques, for accepting this invitation, for giving us this talk. And the floor is yours.
Thank you very much. Thank you for this nice introduction, René, and good morning to everyone. So I'll just maybe remove this. And so yeah, I'm very happy to be here. Thank you for having me here, and I'm very excited to give this talk about disk and planet formation around post-main sequence stars. And as René said, I started my research on on protoplanetary disk around young stars and studying them observationally to study the initial conditions for planet formation. And in the recent years, I discovered that actually some evolved binaries host also very similar disks of dust and gas. And so I'm studying them observationally to compare them to the disk around young stars and to see whether those disks are forming planets or not. And so, of course, I'm looking for exchanges and ideas about this topic as it's relatively a new way to study planet formation in such exotic environments. So, of course, here all my collaborators with whom I'm working towards understanding those disks. So let's start, if it works. Okay, here we go. Now it should work. Okay, all right. So planets. So now we know more than 5,000 exoplanets, and most of them, the very vast majority, in fact, is formed around the stars when they were young. And actually, they are forming protoplanetary disks that are disks of dust and gas that we find around young stars. And to understand all the diversity of the population of detected exoplanets, we can study protoplanetary disks in order to have the initial conditions, so the physical conditions in which those planets formed, but also to look for signs of ongoing planet formation. And so in the recent years, with the advent of observatories like ALMA, but also very large telescope, we start to have specially resolved images of those disks. And they really revolutionized the field because we see a lot of substructures in those disks. So we see, for example, with ALMA in the radio, we see the gaps and the rings in one of those disks. With indirect imaging in the infrared, in polarimetric imaging, actually, we can see some spiral structures and more chaotic structures in those disks. We can see also disks that have very large cavities that are probably due to a companion. And we also start to see asymmetries at the very inner regions of protoplanetary disks, as roughly 1 astronomical unit from the star. So we have all the tools now to really image the disk and use this information to constrain our planet formation theories. And there are several questions that are now really hot in the community, is that how fast those planet forms, and also to know whereas those substructures are related to planet formation. Will they form planets, or are they due to already form protoplanets in those disks that perturb the disk and make this asymmetries? But today, I'm not going to talk about disks around young stars, but more about disks around evolved stars. And can we form planets around evolved stars? Actually, some of the planets can be detected around evolved binaries. So here there's one example, the unanswered system, that is a binary, an ecliptic binary of a white dwarf and M dwarf. And you can, people started to follow up the eclipses of this binary, and they start to find out that there is a very small delay between at each eclipse of just a few seconds. So here you have the cycles, so the number of orbits, so basically time in the x-axis. In the y-axis, you have the delay from eclipse to eclipse. And you see that the time scale is just few seconds, but the eclipses are not very regular. And so to try to explain that, people have fitted a model with a planet, actually two planets, that will perturb the inner binary just by just gravitationally. And because of that, because of the light travel time effect, it will generate such a shift. And so they fitted the data up to end of 2010, and they extrapolate this model to other orbits, and they followed up this target, and they saw that actually the observations are really following the prediction from this planetary model. So these planets are very, I think, the most robust to be detected around such a system. And so people started to find out whether those planets are dynamically stable, and if they could have survived the giant phase of what is now a white dwarf. And they found out that they could not have survived this giant phase because the orbit would have been unstable. And so those planets are very good, actually the best candidates to be formed as a second generation, so in the disk around this binary, but when the white dwarf was a giant star. And so the best model is with two planets with 2 and 7 Jupiter masses at 3 and 5 AU roughly. And a few years later, they started to look for dust, so from debris from the disk that could have formed this planet, and they detected some dust with ALMA in this system. So that's very promising. And we wanted to know if we observe actually such disks that could form those planets. And of course, the answer is yes, because it's actually the topic of my talk. So we see the best candidates for second generation protoplanetary disk around post-AGB binaries. So what are post-AGB stars? So here you have a HR diagram. So you have the temperature increasing to the left and the luminosity increasing to the top. And you see you have an evolutionary track for one solar mass single star. And you see that the post-AGB phase is between the giant branches and the white dwarf phase. So it's a transition phase where the star has really the highest luminosity of its whole evolution. And however, this is for a single star, as I said, but if you put a companion that is close enough, it will perturb the primary when it's a giant. And so you can have interaction, binary interaction. So it could be just tidal interaction or Rush-Lobe overflow, but it can also be a common envelope evolution. And so it will interrupt the giant track because the envelope will be lost earlier than around just if the star was single, and we start this post-AGB phase earlier. And so the core of the star will contract and become a white dwarf a bit earlier. But what we also know is that when you have a companion, this binary interaction, whatever it is, it's not very well constrained, will form a circumbinary disk. And so we know about 85 of those post-AGB binaries in our galaxy, and there are around 200 also post-AGB binaries in the LMC and SMC. So the problem here is to know very well the distance to those targets. Other binaries, the distance may be biased, and then the luminosity as well, and so it's difficult to assess if such a system is a post-AGB binary or not. Okay, so I told you that when you have a binary, you form a disk. But how do we know that? Well, people started to look at the photometry, the spectral energy distributions of all the post-AGB targets, so the single stars, binary stars, and they found something like that. So here you have the flux in the y-axis, the wavelength in micron in the x-axis, and in the visible, you can fit the SED of a photosphere in black. And you see that in red, in the infrared, you have an excess for those targets. And you have two types of excess. You have a shell-like excess, where you can actually fit just a black body at a single temperature. And so actually the infrared excess is coming from the dust. So if you put your dust grains at a given distance from the star, like in a shell, you will obtain just a single temperature black body emission. But if you have a disk, so you put your dust grains at different radii from the star, you have several black bodies that will add up and it will form this kind of smooth infrared excess, very similar to what we see around young stars. And when people started to monitor those targets with radial velocity to look for binarity, this way, they found that the shell-like excesses are always single. We never find a second body in those systems, but we almost always find a secondary in the systems where they show a disk-like excess. So it's a very strong empirical and observational link, actually, between binarity and the presence of the circumbinary disk. Okay. Another feature that I wanted to mention about those targets, and I will come back to it at the later in the talk, is the chemical composition of the post-AGB star. So the post-AGB star is now almost a white dwarf. It starts to contract, and so we can look at all the elements that are on the surface of the star. And so here you have the abundance of each element, and on the x-axis you have the condensation temperature of these elements. And you see that there is a depletion for elements with higher condensation temperatures. So basically, there is a depletion for refractory elements compared to volatiles that stay constant. And that's very interesting because it was interpreted as the fact that you have reaccretion of this of the matter from the disk onto the post-AGB star, but somehow the dust is trapped in the disk and only the depleted matter, so only the volatiles are accreted onto the post-AGB, and this is what we see when we observe this kind of refractory depletion on the surface of the star. Okay, and for example, here iron is not tracing the metallicity of the target, but it's rather tracing this depletion of refractory elements because the metallicity is actually washed out by this phenomenon that dominates what we see observationally. Okay, so here are some of the properties of the system that are summarized relatively quickly. So the disk formation process is the binary interaction. So this ejection of the stellar atmosphere, and some of this ejection is bound to the system in the orbital plane of the binary. So we systematically have a binary at the center. The central star is a post-AGB star, so its high luminosity is at the top of the HO diagram. We have some signs of accretion and outflows. So for example, the chemical depletion is an indirect sign of accretion, but we also see jets from the secondary and outflows from the disk. And those targets are isolated because they are evolved. They are not in a star-forming region, and that's actually quite interesting for testing some planet formation processes. And so the disk properties themselves, so we have this infrared excess that is disk-like. They are stable as seen from the CO observations in the radio with ALMA and Platot-Bure interferometer. So here I have an example of such an observation when you can fit a Keplerian disk. The disk mass is around 10 to minus 3, 10 to minus 2 solar masses. Actually, in dust, some of them has 10 to minus 3 solar masses, so they are quite massive and very comparable to what we see on young stars. You have some evidence for dust growth for some of the targets, and but the disk lifetime is believed to be quite short because this post-AGB transition phase is expected to be relatively short, and when the white dwarf becomes very, very hot, it starts to photoevaporate the disk. All right, so why do we care about those systems? So traditionally, we those systems were studied because of stellar evolution, and more specifically because of binary evolution. Why? Because we are just after a binary interaction phase, and so we can directly observe the products of this binary interaction, which is very difficult during the AGB phase because you have all the dust around and you have convection of the stars. So if you want to detect a secondary, is very difficult from radial velocity, whereas for post-AGB stars, it's way easier. And so, for example, you can study the product and see what is the distribution of periods that you can expect from binary interaction. So, for example, if the two stars go through a common envelope evolution, you expect the orbit to shrink because the secondary is spiraled in, and you expect it to be circular. But if they are more separated and they just go through wind interaction, because of the mass loss, the orbit will widen. So we expect to have this bimodal distribution of the periods. And so from the results from the radial velocity survey, what we find is this. So we see that the distribution of periods is really between the two peaks where we do not expect to have actually the binary orbit. So there's something that we do not understand from this binary interaction, and that's why those targets were interesting to study. There also are progenitors of planetary nebula, so those beautiful images that I'm sure you know. And if you have a bipolar planetary nebula, it's also expected that it could be due to a binary at the center. Okay, but today I will not talk about this. Actually, I will talk more about disk physics and planet formation. So I will focus more on the disk itself, because it's really a new laboratory to study disks physics and planet formation physics in a very peculiar parameter space. And so we can test different theories. We can test the time scales, what happens when the central star is very luminous, and what happens in the presence of planets that are already there before the second generation disk forms. And so we can see if the dust grain can grow very fast or not, because they have to grow before the disk dissipates. We can look for substructures in the disk, and ultimately we can also look for planet formation efficiency of those disks. But before going to that, we need to answer some very interesting questions about the disk processes. And so maybe to go more into detail, I can just detail a bit more some of the things that we can test in this disk. So, for example, the time scales. So from the study of disks around young stars, we start to see that, for example, the masses of class 2 disks. So class 2 disks are all the disks that are older than 1 million years. They are not massive enough to produce the observed population of exoplanetary systems. And we find enough mass only in very young protoplanetary disks that are just a fraction of a million-year-old. So planet formation might happen very, very quickly. We also start to observe substructures in disks like rings and gaps in very young objects. And by studying post-AGB disks, we know that everything that we find in this disk, the substructures for grain growth, must have happened in a fraction of a million years. So we will actually test if the formation of substructures or grain growth is quick enough to form planets so quickly. Also, in the last few years, we start to see that there is an interaction between protoplanetary disks around young stars and their star-forming environment, when you can have some episodic reaccretion of matter from the environment onto the protoplanetary disk, and that can perturb the disk and also trigger a new episode of planet formation. So that's very interesting, but this is something that will not happen in post-AGB binary systems because they are isolated. So everything that we see there, every structures that we see there, we cannot invoke this reaccretion of matter onto the disk. And the last thing that I wanted to highlight is the influence of planets on planet formation. So there is a chicken and egg problem in planet formation theories, is that where if you already have a giant planet in the disk, it will perturb the disk, will make some locations where there's a high gas pressure and where the dust grain can grow very efficiently. And so you can make planets more easily if you already have a planet in the disk. And actually, this is something that can happen in the second generation disks, because the first generation planets could have survived the giant phase, can still be there from the start when the disk forms, perturb the disk, and actually maybe enhance the planet formation efficiency, or at least the disk grain growth in the substructures. Okay, so that are the just few things that I wanted to highlight, but of course there are many other ideas that we can test there. And so, as I told you at the beginning of my talk, I want to investigate that observationally. And so in order to do that, I want to have images of those disks. And to have images, we need to spatially resolve the target, and we need to know what are the scales that we are talking about for those targets. So this is just a schematic, an artistic picture of such a system. When you see the inner binary here, you have the post-AGB here, you have the main sequence star here with an accretion disk, some bipolar outflow, and you have circumbinary disk with some spiral structures. There's even the planet there. Of course, it's an artistic impression, but and the separation between the two stars is roughly 1 astronomical unit. The inner disk radius in dust is 10 astronomical units. Because of the high luminosity of the star, the dust sublimates relatively far from the central binary, and the outer disk rim in dust is around 100 astronomical units. It's just to have an idea of the scales. And so the typical distance to those targets is 1 kiloparsec. So that's very handy, because at those distances, 1 astronomical unit is a thousandth of an arc second, or 1 milliarc second. So if you're able to have a 1 milliarc second resolution, you can resolve 1 astronomical unit in these systems. And we are quite lucky, because we have actually all the instrumentation to do that, to have the images of those targets. For example, for the inner parts of the disk and the inner binary, we can use near-infrared interferometry at the VLTI with instruments like PIONIER and Gravity. We can probe the inner regions, and you see that at this wavelengths, at 2 microns, we can probe the very start of the infrared axis. In the mid-infrared, we can still use VLTI with the MATISSE instrument, where we probe the inner disk region up to 10, 20 astronomical units. And with ALMA, we probe the outer parts of the disk in the midplane, and also probing larger grain sizes that in the infrared. And we can also add scatter light observations with instruments like SPHERE, for example, where we probe the disk surface, or the small grains, or the disk surface that are scattering stellar light. And so we can really probe the 3D structures of those disks and study them for and characterize them in detail. So in the first part of my talk, I will mostly focus on the VLTI observations of those disks, and in the second part, I will rather focus on ALMA and SPHERE ongoing observations. All right, so after this quite long introduction, now I can start to show you some results that we got. So I will start with an image on one such a system. Then I will go to the surveys to see if this system is representative of all those post-AGB targets. I will talk about the very recent exciting discovery of transition disks around those targets. So transition disks with very large inner cavity. And then I will go towards observational perspectives. All right, so let's start with one target, RSO8. Okay, so RSO8 544-4431, I will just say RSO8 in the rest of the talk, is a binary. So here you have the radial velocity with time with a model that is fitted, and so you have a period of around 500 days, a moderate eccentricity of 0.2, and you have the spectral energy distribution with a wavelength that is really disk-like, that shows a nice disk-like infrared axis. And so we gathered a lot of observations with the VLTI in the near-infrared in order to characterize the very inner structures. And if we apply conventional image reconstruction, this is what we get. We just get a very bright blob at the center, and this is the primary star that emits around 50 to 60% of the light in the infrared. And then we can use a special technique called sparkle, where we subtract the central star, and then we can reveal its environment. And so that's very nice, because we can see two things. The first one is the point source very close to the post-AGB star, and it's at the location of the secondary. And this is unexpected because the secondary is a main sequence star, and so the luminosity of the main sequence star compared to the post-AGB star that is 10,000 solar luminosity is, I mean, the contrast is so huge that we are not expected to see that. We think that we see the accretion disk instead around the secondary. That is roughly a 1 astronomical unit from the primary. And we also see this very nice ring, which is the dust sublimation front of the circumbinary disk. We can also remove the secondary with sparkle, and we see that the inner rim is at a radius of 8 astronomical units. And it's also not axisymmetric. So we see that there is one maximum on this side, which is kind of expected because it's the side where the post-AGB star is closest to the disk. So because of the illumination, you have one side that is brighter than the other, but you have also other maxima on the other side that could be due to disk binary interactions or a spiral wave, for example, going to the inner rim. We also have the temperature, which is roughly consistent with the dust sublimation at this for this target. Okay, so this is just the image, but then we use the radiative transfer model to model the visibilities in the near-infrared, but also the spectral energy distribution. And we use MCMax, which is the radiative transfer code that is usually used to reproduce or to model protoplanetary disk around young stars. And it reproduces very well, as you can see, the spectral energy distribution, but also the visibilities from PIONIER. And so this is the model in the surface density with radius. So you see that you have the dust sublimation at 8 astronomical units. The binary is here. It increases, the surface density increases up to a certain radius, and then it decreases as expected in protoplanetary disk. And the dust mass is around 10 to the minus 3 solar masses for this model. Of course, it's a very crude assumption because we only have near-infrared spatially resolved information and the SED, but it's roughly in the right ballpark. So they are quite massive, those disks. And we follow up this disk with all the instruments that we have at the VLTI. So we have here the visibilities with PIONIER at 1.5 micron, here with gravity at 2 microns, in L-band at 3 micron with MATISSE, and also at 10 micron also with MATISSE. You have the visibilities in blue, so the data in blue, and in orange you have the fit of the geometrical model, and so it roughly reproduces quite well the data. And here, this is the image from the geometrical model fit. Okay, so you can see that for the near-infrared wavelengths, a Gaussian with a single temperature reproduces the data quite well, but at longer wavelengths, you need a model with a gradient in temperature and in radius to reproduce the data. And so this is the work of the PhD student at K11, Ake Corporal, and she interpreted these observations as evidence for a disk that is not flat, but is more rounded, puffed up at the inner rim. And so the emission surface at the inner rim is very large. So that's why we are dominated by one single temperature in the near-infrared. And then in the mid-infrared, we start to probe the rest of the disk. And that's why the models with the gradient in temperature in radius are reproducing the data better. And now she's working into having a full radiative transfer model to reproduce all the data at once. So starting with the model that we had from near-infrared, but then trying to reproduce all the wavelengths, which is actually quite complicated, but she's having nice results. So stay tuned to know more. Okay, so this is the results on one target, and wanted to know if this target is actually very representative of the whole population of post-AGB binaries. So we started to make surveys with the VLTI in the infrared, and here is a survey that we made with PIONIER, so at 1.65 micron. We had 23 targets. And so we probed the disk, inner rim, and the inner binary. And here are the images from geometrical models. So we cannot do image reconstruction because it was a snapshot observations. We don't have enough UV coverage to have an image. But these are the images from the fit of the geometrical models. And here are the main conclusions that we had from the survey. The first one is that the inner rim of the circumbinary disk is ruled by dust sublimation. And so we determine that by putting the size of the ring that we fitted to the data against the luminosity of the central of the post-AGB star. And if you have the sublimation radius at a given temperature, let's say 1500 K or 1000 Kelvin, you expect that the size is scales with the square root of the luminosity of the central star. And this is what we obtained. So in purple here, you have the post-AGB binaries. And in blue-green, you have the young star objects. And you see that they are following the same trend. However, it seems that there is a small shift that could be due to a different mineralogy of the dust. In this disk, for example, here the dust grains can sublimate at a lower temperature and so have a larger radius, but also it depends on the local density at the dust sublimation region. Yeah, and the truncation radius from the inner binary is always smaller, or in most of the cases, smaller than the dust sublimation radius. We also saw that the disks are continuous in radius. So we compared the size in the near-infrared with PIONIER with the sizes at 10 micron with MIDI in the mid-infrared. And we compared that to models, very simple models of just continuous disk with gradient power law in the temperature with radius. And in the yellow area here, we expect all the continuous disk. And you see that most of them are falling in this yellow area. Here you have an upper limit. There are some outliers, but those targets are compatible with a continuous disk in the first 10, 20, at least astronomical units. And the last conclusion that we had from the survey is that those targets are very complex. The emission morphology in the near-infrared is very complex. And we saw that because we started to fit very simple models, and then we increased the complexity, and we have a test to select the best model with a penalty for the number of parameters. And despite this penalty term, most of the targets needed more than 10 parameters just to reproduce the data, because the signal in the closure phases in the visibilities was so complex that we needed very complex models. So it also means that we are probably biased by the geometries that we put in our models, and to really investigate those targets, we need to do imaging and not just a snapshot survey. And this is something that we started with a large program that I will talked about in the last part of my talk. But before, I'd like to talk to you about this transition disk around the binaries. And so this is the very recent results that we had. So transition disks were first discovered around young stars, and those are disks with a very large cavity that is several times larger than the dust sublimation radius, like 5, 10, or 20 times larger. And so the causes of this cavity can be, there are different interpretations. One of them can be photoevaporation. So we have high energy photons from accretion on the central star that start to photoevaporate the inner parts of the disk, and hence creating the cavity, which can also have disk-planet interaction. When you have a massive enough planet in the disk, it will start to make such cavity. So this is around a young star. And around post-AGB binaries, we actually modeled one such an object where we find such a large cavity. So we can see here the spectral energy distribution, so the flux against the wavelengths, and you see that the infrared excess does not start in the near-infrared, but starts at longer wavelengths at 3, 5 micron. So it means that there is no dust at the dust sublimation region. And this target was resolved with mid-infrared interferometry, and the size of the cavity was fitted to the data, and it's about 34 astronomical unit, which is like 7 times larger than the dust sublimation radius. And so a radiative transfer model was also fitted to the data, confirming this radius, and you see that the theoretical sublimation radius is 5 astronomical units. So there is another thing that is making this cavity very large. And we wanted to know if this disk, this transition disk, is unique around post-AGB binaries, or if there is a population of them. So we started to look first at the SED, spectral energy distribution, and characterizing the infrared excess. And we see that for a full disk, if you look at the color in the near infrared, you'll have a strong color in the near infrared for a full disk, but a weak color for the transition disk, where in the mid infrared you have a strong color for transition disk and a flat spectrum here for the full disks. And so we took all the 85 post-AGB binaries that we know of in the galaxy, and we put them in this color diagram, where you have the near infrared color here and the mid infrared color here. So the full disk is here at the center of the diagram, and the transition disk AC here is here in the bottom right part of the diagram. And so the first thing that we see from this diagram is that there is no random distribution of the points, but there is some structure here. And also that AC here is not alone in this diagram. So there are other targets that are also similar to AC here, where there is a very strong mid-infrared color, but almost no near-infrared excess. And so to make sense of this diagram, we also use radiative transfer models of full disk and transition disk, where we varied some parameters like the inner radius, some dust grain properties, but also some density structures to make this population, this cloud of points, and put them in this color diagram. You can see that here you recover all the full disks, and the transition disks are at the bottom and right parts of this color diagram. And so to make sense of this, we did something that is very classical where we first want to characterize something. We just put boxes in this color diagram just to make sense of what we observe. So they are quite arbitrary, but also guided by the radiative transfer models. And then we build up the SED, where we normalize all the spectral energy distribution in 1 micron, and we just characterize the infrared excess. So here in black, you have the median infrared excess of all the disks. And in the gray area, you have the 25th and 75th percentiles of the infrared excesses. So it means that half of the targets have an infrared excess that is in the gray area. And so if you look at the center of this color diagram, you see that you have most of the disks are here. They are full disk, and you see that the median of this category, which is called category 1, are really following the median of the full population. It's normal because this is where most of the disks are. If you look at category 0 disk, you see that the infrared excess is very, very strong. And actually, we interpret that as just evidence for inclined disks. And so we know that most of the targets are actually very inclined. Then we have those category 2 targets when you have AC here, and we see that there is no near-infrared excess for all of them, but there is a very strong mid-infrared excess that is even stronger than the median of the whole population. And so it means that you have a large cavity, and that the inner rim is directly exposed to the photons from the star. That's why it's puffed up and it emits a lot in the mid-infrared, more than in the other types of disks. Then you have category 3 when you think that there is a lack of near-infrared excess, but it's not very, very clear. And you think we have a mix of full disk and transition disks. And at the end, we have category 4 targets where the infrared excess starts very, very late, and we think that is something like a debris disk, so a disk that is dissipating. And so we can see that actually the boxes that we define are very good into classifying the infrared excesses, so that's very convenient. And the first conclusion that we can have is that around 10% of all the disks have a large cavity. So there are transition disks around binary target. But that's not all the story, because we started to look for correlations between those categories and other observables. And we found that actually the chemical depletion of the refractory elements that I talked about at the beginning of the talk. Here it's tracing by iron, but we have also other elements that are showing the same trend, just iron is more easy to measure. We see that for transition disks, the depletion is stronger than for full disks. And so what does it mean? It means that for targets, when you have this large cavity, the dust is more easily trapped in the disk, and the depleted gas is accreted onto the post-AGB star without the refractory elements. And so the most easiest way, let's say, to make at the same time the cavity and trapping the dust is to put a giant planet in the disk that will perturb the disk enough to form the cavity, trap the dust, and accrete the depleted gas onto the post-AGB star. And what's interesting is that the same thing is seen around young star objects that have a transition disk, or where there is a substructure in the disk because of planet formation. And it's most easily seen around intermediate mass stars that have a radiative envelope, where we can really probe the chemical peculiarity on the surface of the star and relate it to what is accreted from the disk onto the central star. So that's quite exciting. It's still a hypothesis. It's the most likely that we have so far, and it needs to be tested with some more observations. And so now I'll go to the second part of the talk, which are observational perspectives. And I will first talk about this VLTI large program that is called INSPIRING, that stands for Interferometric Survey of Post-AGB Binaries with their ring. And it's 250 hours of observations with the VLTI, with PIONIER and gravity on 11 targets. And the goal is really to have image reconstruction to not be biased by geometric models, because the morphology is so complex. And we want to recover the structure of the inner rim, see how it changes with orbital phase of the inner binary, and also see if we can detect the secondary in also other targets, this secondary accretion disk. And so for this, we develop a special methodology for image reconstruction, where we not only use the Bayesian framework, like in classical image reconstruction approach in infrared interferometry, but we also use neural networks to define the Bayesian prior for the image reconstruction. So here, the neural networks learned from images of radiative transfer models with very, very different parameters for the orientation, the density distribution, the dust grain growth, and we use this prior in the image reconstruction. So the radiative transfer models were all axis symmetric, and you see that for RS08, you can still recover the non-axis symmetric structures, because the data is telling us that there are some non-axis symmetry, and you see that the quality of the image is better recovered, and we can see the asymmetries in a better way. And so this was developed by Rick Kless, who was a student at K11 at that time. It's an organic software. And so from the image will inspire us the geometrical models. And we use the geometrical models to retrieve the size, the temperatures, the orientation of all the components of the image. And then we'll use that as an input to the radiative transfer modeling to get the physical conditions in the system. Of course, this large program started just before COVID, so it was a bit delayed. And it's very difficult because in infrared interferometry, we have just 4 telescopes. And so we need really to have a lot of observations to fill our UV plane. And if you interrupt the filling of the UV coverage, and because those are binaries, we have to start again because the binary phase already moved. And so it's still ongoing, actually. But we already had some images on some of the targets that I'm happy to show you today. So you see here that actually the morphology can be very, very complex, more complex than the geometrical models that we fitted. So for example, here we have this double ring structures. We have some more simple ones where we have the inclined disk. And here, for example, we cover the primary, the secondary, but also the circumbinary disk, which is here. And this is a large structure that we're still not sure to understand, probably linked with an outflow that we see at very large scale with ALMA in the CO. And we also managed to get some images of RS08 at different orbital phase, so we could follow up the binary and the reaction of the disk to it. And this is just for comparison. We did a similar large program on protoplanetary disk around intermediate mass stars, and this is the images that we got. And you can see that even if the intermediate mass young stars are closer to us, because of the difference of luminosity, the inner rims are not as much resolved as the post-AGB binaries that are way further from us, but are so luminous that we can really resolve the inner rim. So that's quite nice. And for IRAS-08, we're able to make images at different orbital phase. We can see here that post-AGB is in white. The secondary is redetected at each period at different locations, and can see that the second binary disk is more luminous on the side of post-AGB. So this is with the classical image reconstruction, and this is with the neural networks when you really recover this variation of the luminosity of the brightness of the disk with orbital period. Okay, so this is for the very inner regions, but we also started to probe the outer regions, and this is the work of Katarina Andrich, who is a PhD student at Macquarie University, who is working with sphere observation of those targets. And we also see very different morphologies from the targets that we observed. For example, here you have a very inclined disk when you see the top surface of the disk, but also the bottom surface on the other side, and the center you have the shadow because the disk midplane is very dense, and we see the shadow, so that's quite cool. But we also have some more complex morphology, like another rings around the disk, or just the disk alone, or some more complex things. And here we have an arc, and this actually is one of the transition disks, so disk with a large cavity, where we really resolve the inner disk rim even with direct imaging observation. So that's quite cool. So stay tuned, because Katja will publish this paper quite soon. And we also started to resolve the dust of those disks with ALMA. And you can see here the image of IRAS-08, when you see that there is quite large grains up to a radius of 100 astronomical units. So there are really large disks, very comparable to what we see around the young star, and they are also they have a very similar mass. And here the white circle is actually the dust sublimation radius as imaged with the VLTI with PIONIER. So you can really start to have all the different scales for this disk, and so you can really constrain the full 3D morphology of the disk, from the near-infrared with the VLTI, the mid-infrared with the VLTI, the disk surface with a sphere in the infrared, and the ALMA radio observations of the millimeter dust. And so the goal now is trying to find a model that reproduces all the observations at once, and that's actually the most complex task, but also the most interesting one. And we can really make nice links between the different scales that we are probing. So here we have an image of one such a disk, where we see in CO this hourglass-shaped structure. You have the bipolar outflow, you have the disk in green here, and with PIONIER, we at very different scales. So here you see that it's a zoom of 1,000. We see the inner rim of the disk, and the second ring that is probably above the disk midplane, and that could be the start of the outflow that we see at a very large scale. You see, it's also shifted towards the blue part of the outflow. But of course, it's still difficult to make the link because the scales are so different. But maybe we really start to see the basis of this outflow. And with sphere, I showed you this image with the top surface of the disk and the bottom surface. And with the VLTI, we see that these complex structures in the inner regions is really erasing, and we need to make sense of that and combining those data together to get the full disk structure. All right, so this is for the near future. We're analyzing all this data together now, but for the midterm or long-term future, we want to know if we can detect actually the planets that may be formed around this second generation disk. So we want to look for second generation planets that we should find around the double binary white dwarfs. And so there are two ways to look at them. The first one is to use the ELT, because we have the sensitivity to look for binary white dwarfs that are quite faint, but also angular resolution to look for these companions. But also we can do that with gravitational waves. And so actually CAMIA is working on that. And so we expect to detect some planets about double white dwarf. And we are now working with CAMIA in order to know if we will be sensitive to a second generation of planets that are formed in disk like the post-AGB binary disk, and if we're sensitive to this population in what we will detect with LISA. So that's very, very interesting, a very nice future. Okay, so here are my conclusions. So I hope that I managed to convince you that post-AGB, the disks around post-AGB binaries are very similar to disks around young stars, and they are actually very interesting to study because we can study all the disk processes and the planet formation processes in a different parameter space. And so we can really test the different theories in these extreme environments. And you start to see indirect signs of planets in these transition disks, and the fact that there is a link between the structure of the disk and the chemical composition on the surface of the post-AGB star. And we started a thorough observing campaign to really get the full 3D structure of the circumbinary disk, and especially instruments like MATISSE on the VLTI and ALMA are very powerful to start to study those transition disks to really confirm this inner cavity, to measure the size of the inner cavity of the disk and see if there are some perturbations due to a planet, and confirm this exciting hypothesis. And I will finish on those conclusions. Thank you very much.
Thank you very much, Jacques, for this wonderful talk. So now the talk is open for questions. I think Camila will manage the questions over there. And I will tell you if there is a question here soon.
I need a microphone.
Okay.
Yes. Congratulations, very remarkable results. I had a concern because you say that the cavity can be created by protoplanets, a second generation in this. It could be, but I wonder, you had detected some transitional disk in this post-AGB stage, no? But in the case of protoplanetary disks, the luminosities are around 10 solar luminosity 100, no more. But in case of post-AGB stars, you mentioned that the luminosities goes 10 to the 4, 10 to the 5 solar luminosities. I wonder if planets can create cavities in this case, how planets can survive for the high temperatures, because for a system with a total luminosity is 10 to the 5, you will have a very high temperatures inside these cavities. In case of the gaseous, like Jupiter planets, will evaporate. No? So I think the mechanism to create this cavity is not planets, could be another, for example, because I had this concern with the temperature. Also, I had calculated the sublimation border for the case of massive protostars, which has similar luminosity. I remember, if I remember well, the size of this border of the radius, the sublimation radius, is about 50 AU or 100 AU, but you can estimate a lower value, no? I wonder how do you estimate? I remember if you plot only 10 or 10 AU for the case of a central star of 10 to the 4 solar luminosity. No? Sorry for question.
All right, so so maybe to the first remark, so the cavities are quite large actually, because
planets can survive at high temperatures if they can create this cavity. Because we are dealing with a very high luminosity in the phase, 10 to the 4, 10 to the 5.
Yes.
For the case of the planetary disk, transitional disk, we have lower luminosity. And
Yeah.
planets can survive inside the star. But for the cases post-AGB stars, they are very luminous. And I think it should be other kinds of planets, not gaseous planets, no? Like Jupiter planets. I don't know if you understand my point.
Yeah. So how can gaseous planets survive such a high, high temperatures? And so in the transition disk, the inner rim is way larger than the dust sublimation. So the temperature of the dust at the inner rim of the transition disk is several hundreds of kelvins, it's less than 1,000. Because the 1,000 Kelvin we measure the temperature of 1,000 Kelvin at the dust sublimation radius. So at a 30, 40 astronomical unit from even such a luminous star, I do not expect the temperature to be that high, actually. And there is, those stars are very cold. They are not warm. Okay, they are like 4,000 Kelvin. Yeah, and so here the sublimation temperature is 1,000 Kelvin.
Because you have this high luminosity.
Yeah. So 1,000 Kelvin is for the dust sublimation radius, but for the transition disk, the radius so the temperature should be lower, so a few hundreds of Kelvin. I think we measured that for the. Yeah.
The radius of the ring, or the radius of the cavity was about 5 TU, no?
Yes. Yeah. But the.
I guess planets cannot survive, at least gaseous planets cannot survive inside the star.
Yeah, that's for sure. But this is a full disk. This is not a transition disk. So what I call a transition disk is where the cavity is way larger than the theoretical dust sublimation radius. So I agree that inside here, yeah, it's very hot, and so the planets will not survive. But this is a full disk. A transition disk cavity will be 5 or 10 times larger than that. And so here you have room to put a planet that can survive even a high luminosity of the central star. And so that's the point. So this is the cavity that we expect for full disk, actually. And so here in the infrared, the survey that we done is really only full disk, because the full disk are bright in the infrared, but the transition disk are not present here in this survey because they do not emit in the infrared because there is no dust there. And so the one that we measured here, this one, the cavity, you see that the sublimation radius is expected at 5 AU, but the radius of the cavity is 34 AU, and here the temperature is. So this one, I have to check exactly I can give you the number, but yeah, but it depends on. Yeah, but actually, so here the no, for this it's really so we just follow the relation that we got for the full disk, so this one, and we extrapolated this to get this radius, and we measure something that is way larger than that. And so it's for this kind of disks that we think that the planet can be somewhere over here and make the cavity, but also trap the dust in the outer parts, something that photoevaporation will not do, or other processes that we know of. Maybe there is one, but it's for the moment, this planet hypothesis is the most likely, given what we know from the studies and the simulations of protoplanetary disk on young stars. And now we have the observations on this transition disk to confirm, to get the size of the cavity, and also see if a planet can reproduce the cavity and the structures that we will obtain from the observations. Yeah. No. Yeah, we can talk about that, but actually, yeah, I would, yeah. So here we have a small accretion disk around the secondary that we detect. And actually, this is the point source, but it's very small because it has to fit in the row slope of the binary. So the separation is 1 AU, so the disk here is about 0.5 AU, so it's a very small one. So this is the typical separation, is 1 up to 2 maybe AUs from this those targets. But yeah, I mean we just use the same relation from the dissemination radius as for young stars, and even a bit higher than that. So this should scale with the square root of luminosity. So you see that, okay, we can have 10 AU radius, but or some high luminosity you have 20 AU in a radius, but we cannot reach more than that. But we can discuss that more in detail. Yeah. Yeah.
Any more questions? Yes.
So in these disks that you call transition disks, is that, as you mentioned, if I understood correctly, is that the inner cavity is larger than the sublimation radius. But how do you know that the rings that you see are actually stable Keplerian disks if you don't have kinematical information? Because in some post-AGB stars, what you see with line observations are expanding rings. So in that case, with time, the inner cavity will be larger naturally than the inner sublimation radius. And in your ALMA observations, you plan to observe dust emission. Do you plan to observe lines? Because kinematics, I think, will be important to fully understand these disks. Okay.
So yeah, you're right. To know if those disks are stable, we need to observe the Keplerian rotation. But actually, we do that with ALMA and Platot-Burr interferometer observations at a bit larger scale than the dust. But we see in the inner parts Keplerian rotation, and in the outer, very large, very far from the binary, we see still expansion and some winds, but like at 1000 AU. But in the inner parts, we see Keplerian rotation. I mean, not all of them, but those that we could observe so far. So I think there are like, we observe like 10 or 15 of them, and we see in the inner parts Keplerian rotation. But also we have always dust at the innermost radius where it can survive. So it means that it's not expanding, but it's staying there. There's still always dust at the dust sublimation radius. And you also have the signs of accretion onto the central star with this chemical depletion of the refractory elements. We see a jet around the secondary, so it needs to accrete, and the post-AGB star there is no super wind anymore. It's not an AGB star, it's a post-AGB star. So there is not enough mass loss from the post-AGB star to feed the circumsecondary accretion disk, and so the mass must come from the circumbinary disk. And we are now actually looking for a direct tracer of accretion, so some lines that could indicate that in the inner parts we have to really constrain the accretion that we have from the disk onto the central star. And actually, so we see the jet in absorption in H alpha from the secondary, and the secondary is passing in front of the post-AGB star. And so it creates a shadow in H alpha. And we modeled, so there is a student in K11 that modeled those jets, so we can have the velocity and the density of these jets. And he estimated the amount of accretion that we need to have this amount of outflow. And so we need really accretion from the circumbinary disk to feed the secondary jet. So we have Keplerian rotation from CO, but also signs of accretion in the inner parts of those disks. So, yeah.
Thank you for this nice talk. And I have a question. In protoplanetary disk, one of the explanations that have been considered from the very beginning for the presence of cavity was the presence of a binary, because when there is a binary, the tidal interactions create a cavity. However, there is a relationship that can be modeled between the separation of the binary and the radius of the cavity. So did you check that, because you had selected binaries, you have that these cavities are not created by the binary itself, but for a different object that you propose is a planet?
Yes, so this is something that we checked with the with this study, where we measured the circumbinary, the radius of the circumbinary disk emission, and we compared it also to the dynamical truncation from the inner binary. And the dynamical truncation radius is always inside, I mean, always. In 99% of the case, it's inside the dust sublimation radius of the disk because of the high luminosity of the star. So if not, we would have a larger scatter in the radii of the dusty disks. But actually, there are few disks, I think 2 or 3, where the sublimation radius is inside the expected dynamical radius, and so this creates a larger cavity. But this we know that it's due to the inner binary. But for the transition disk that we detected, apart from those 2 targets, the others are due to something else. So we need a larger separation. So, but we still need to accrete the volatiles into the inner, onto the post-AGB star, because if not, we'll not see the depletion of refractory elements and no depletion in the volatiles. So the companion has to be massive to trap the dust, but cannot be too massive to still let some gas through to be accreted onto the central star. So so the hypothesis of the third body is really that because the inner binary cannot produce such a large cavity.
Thank you so much for your nice talk. I would like to ask you a question about the time scale of the planet formation. I mean, do you expect it to be shorter or longer? And if it were longer, should be interesting in order to try to test the current ideas about the planetary system formation. Because in that case, I guess that you could observe more in detail the different phases of this process of, I mean, the planetary formation.
Yeah, so that's a good question. It depends on how you form planets, of course. If you want to form them through co-accretion, it will take a long time, and we don't have enough time to do this in those disks from the small dust grains. If you want to form through GI, so if the disk is unstable, it will be fast enough to make them in those disks. But however, those disks are expected to be quite warm. We still need to determine, I mean, one of the key things is to probe the tumor parameters in those disks and see if they are stable. We expect them to be stable. But I think if planet formation happens in those disks, it can be a bit in a different way than around young stars, because you can imagine, for example, that you already have some planetesimal in the disk from the first generation, or even rocky planets, and they are suddenly they are inside a second generation disk, so they will start to accrete. They will go through runaway accretion, and they will become larger planets. So we can have this kind of scenarios where you already have some seeds, or already have another giant planet that can perturb the disk, for example, and enhance the planet formation efficiency. So these are the type of questions that we can try to answer or to progress on by studying what happens in these disks. But without going through GI, I think the core accretion alone, it's way longer than the lifetime of those disks. So that's why it's also interesting to probe those disks, because around young stars we start to see more and more hints that transformation happens actually very, very quickly, much more quickly than we think. Thanks.
René, there are no more questions in the audience here. So, is there something online?
There is no questions here and no questions in YouTube. So I think we can close the talk. Thank you very much, Jacques, for this wonderful talk. I learned a lot on that.
Thank you.
Enjoy your stay here with Camila.
Thank you. Thank you very much. Thank you, René.
Thank you all.
Thanks.
Okay.